The purpose of this presentation is to determine the inside air temperature of a car after it has been sitting in the sun for an hour, and also to use the heat transfer principles and equations to find the rate of temperature change inside the car. There are various studies done by several universities, mainly focusing on child and pet safety, claiming what seems as a dramatic temperature increase inside the car based on sun exposure and ambient air temperature. For example, a study from San Jose University claims that the temperature inside a car will increase 24 degrees Celsius or 43 degrees Fahrenheit in just an hour of sitting in the sun. A professor from San Francisco University claims that children have died in cars where the ambient air temperature was as low as 63 degrees. These claims of significant temperature increase will be tested and proved through analytical calculation. First, we want to explore, however, why the temperature inside the car can continually increase when the ambient air temperature is unchanging. As the car is left in the sun, the inside temperature of the car will continue to increase due to the greenhouse effect. The greenhouse effect refers to instances where short wavelengths of visible light from the sun pass through a transparent medium and are absorbed into objects. Those objects in turn radiate infrared waves that can only partly pass through glass, thereby heating the enclosed environment. This is the exact phenomenon that happens in a car. When the waves of visible light pass through the glass windows, it will heat up the objects in the car, such as the seats and the dashboard, and they will in turn re-radiate infrared waves into the enclosed air. The air in the car is continually trying to reach equilibrium with the temperature of the surrounding objects, and therefore will continually increase as the objects in the car continually absorb energy. 7 tests were conducted in which a thermometer was placed inside a 2013 Hyundai Sonata and left to sit in the sun for an hour. Every test began with the inside air temperature of the car at 29.4 degrees C, with the outside temperature also being 29.4 degrees C, with a standard deviation of about 3.4 degrees. Every 10 minutes, the inside air temperature of the car, the temperature of the dashboard, and the average temperature of the seats were observed. The dashboard temperatures and seat temperatures were taken with a cooking thermometer for better accuracy. It should be noted that all tests were conducted at the same times on different days with similar solar radiation. When the tests were finished, the data was recorded and evaluated. The results of the test showed a linear relationship for all aspects of the data between the increase in temperature and the time in the sun. The figure below shows the data for the increase in air temperature inside the car. It was observed that the average final air temperature of the car was 49.1 degrees C, which was an average increase in temperature by 19.68 degrees Celsius, or just above 35 degrees Fahrenheit, with a standard deviation of 0.437 degrees C. This is a increased temperature rate of about 0.328 degrees Celsius per minute. The trend line of all the data was constructed in order to observe an average relationship. The trend line shows a near-perfect linear relationship with an R-squared value of about 0.99. The results of the test also showed a linear relationship between the increase in temperature of the dashboard and the time in the sun, as well as the increase in temperature of the seats and the time in the sun. The figure on the left shows the data for the increase in dashboard temperature over an hour, and the figure on the right shows the data for the increase in seat temperature over the hour. The R-squared value of the dashboard temperature relationship was 0.99, confirming the linear relationship observation. It was observed that the average increase in temperature of the dashboard was 28 degrees Celsius over the hour, with a final average temperature of 57.4 degrees C, with a standard deviation of 0.968 degrees C. The R-squared value of the seat temperature relationship was 0.98, again confirming a linear relationship observation. It was observed that the average increase in temperature of the seats was 22.4 degrees C over the hour, with an average final temperature of 51.8 degrees C, with a standard deviation of 1.06 degrees C. These data trends were then compared to analytical calculations that were made to find the theoretical inside air temperature of the car and the theoretical change in temperature per minute. The heat transfer equation used was an energy balance equation in which the energy stored in the air is equal to the re-radiated heat of the objects in the car that were being heated by the sun, and the energy lost due to convection because of the steady outside temperature. Only the dashboard and the seats were considered when calculating the re-radiated heat because the other objects in the car gave off considerably less heat due to having a much smaller surface area. An average value of 1014 watts per square meter was used for calculations with a standard deviation of about 5%. First, the dashboard and the seat's final temperature was determined through transient conduction, where the heat transfer coefficients were determined and then used to find the final surface temperatures, which varied from the experimental final temperatures by about 1%. The dashboard and seats had calculated final temperatures of 57.5 degrees C and 52.2 degrees C respectively. With the surface temperatures of the radiating surfaces, the heat transferred to the air over the hour by the dashboard could be calculated by finding the convection coefficient through the use of the Nusselt correlation for horizontal plates. The same was done for the seats by using a combination of the Nusselt correlations for horizontal plates and vertical plates. It was determined that the seats emitted about 3 times as much heat due to a much larger surface area. Then the heat that escaped the car due to convection from the outside air temperature was calculated using the resistance method. With all the different heat transfers calculated, the original energy balance equation could be solved, and it was determined that the final theoretical air temperature was 51.9 degrees C after an hour of sitting in the sun. This is about a 3-degree difference from the experimental value. The theoretical rate of air temperature increase was calculated to be 0.3748 degrees C per minute, varying by about 0.004 degrees C from the measured temperatures. A linear model was constructed and compared to the trend line of the original results. By observing this model, we can conclude that over the hour, this model would be reliable in estimating the inside air temperature of the car. The difference in experimental temperatures and model temperatures could be due to the inaccurate measurements of surface area and/or inaccurate readings from the thermometer. It was concluded that the model was very similar to the experimental data with about an error of 5% after an hour. So in conclusion, we can see that after an hour, the temperature in a car can rise about 19.7 degrees C, which is about 36 degrees Fahrenheit, when a constant solar radiation of a little more than 1,000 watts per square meter is emitted. It can also be concluded that the rate of temperature increase is independent of ambient air temperature and dependent on the initial air temperature inside the car and the intensity of the solar radiation, which means that this rate of temperature change can be applied to any circumstance where similar solar radiation is being emitted. And that concludes our presentation.